Good afternoon, everybody. So I am Sumit. I am an assistant professor in this department. Welcome everyone to the KIAC Distinguished Lecture Series. Today's talk will be delivered by Professor Prabhat Mishra. He is a professor in the Department of Computer and Information Science and Engineering at the University of Florida, USA. He is also a Kotak Mahindra Bank's visiting chair professor at the Kotak IISc AIML Center at IISc. His research interests include AI for cybersecurity, design automation for embedded systems, hardware security verification, and quantum computing. He has published 9 books, 35 book chapters, 30 patents, and more than 250 research articles in premier international journals and conferences. He currently serves as the chair of the IEEE CEDA Fellow Evaluation Committee as well as the chair of the Editor-in-Chief Search Committee for the ACM Transactions on Reconfigurable Technology and Systems. He also serves as the program chair of the International Conference on Hardware, Software, Co-Design and System Synthesis and IEEE International Symposium on Hardware-Oriented Security and Trust. He currently serves as an associate editor of ACM Transaction on Embedded Computing Systems and ACM Transaction on Design Automation of Electronic Systems. He is an IEEE Fellow, a Fellow of the American Association for the Advancement of Science, and an ACM Distinguished Scientist. So let's welcome him. And please don't hesitate to ask questions in between, as he already told he doesn't mind. And there's a surprise after this talk. Okay, there's a reward basically, not surprise. Okay, so what do you?
Good afternoon, everyone. Thank you, Professor Mondal, for the kind introduction. I would like to take the opportunity to thank KIAC IML Center for giving me this opportunity to come here and present. So next 1 hour, I'm going to talk about quantum AI, not in a traditional sense the way presentations are done. Instead, the way I started working in this area about 8 or 9 years ago. So that this talk is prepared for the students. So professors are allowed to take nap or whatever they prefer. So I'm going to present in a way so that just leaving the room, you can start actually one of these areas. And I prefer you ask me questions while I'm talking instead of waiting for the end. So here is a brief outline of my presentation. I'm going to introduce to quantum computing. I know all of you know. And these two words are well searched in Google, quantum and AI. But I'm still going to talk about little bit just to put the context. What is the context of my presentation? Then I'm going to talk about quantum algorithms. That's the starting point. That's where it starts. And I'm talking in a computer science department. And I'm going to focus majority of my talk on the quantum AI. And specifically, I took an application to show how quantum AI is applied there. And if time permits, depending on how I proceed, I'll talk about few other areas that might be interesting to computer scientists and computer engineers. So to start with, before any of us want to work on quantum computing, we want to know what is a quantum computer. Because at the end of the day, that's where your computation is going to happen. So this is how quantum computer looks like. It's really big, it's really cold, lot of wires, and it takes a lot of help from classical computer. So it seems quantum computer is going to solve all the problems in the world, but it needs all the help from everybody else. So it doesn't add up, and that's what I'm trying to clarify. The most important part is this: if you want to buy a quantum computer from IBM, it's going to cost about 100 million, give and take, for a very older version of their computer. So in 100 million, what exactly you are getting? A quantum processor which is sitting somewhere right inside. Just to show you a perspective, this is right about this size. A tiny chip, that's all is quantum computer. Everything else is so off so that you are willing to pay $100 million. Now, what exactly is happening here, I'll talk briefly. But before I do that, I want to tell you one interesting fact. There are so many technologies for quantum computing. I'm more familiar with the superconducting qubit, but there are also different other trapped ion and quantum dots and so many technologies. But the interesting fact is the size of each of them or each of the qubit is increasing over time. In classical domain, if you are working in classical VLSI, you know it used to be micron, 18 micron when I was doing PhD 25 years ago. Then it from micron it went to nano. Now as we speak, it's 3 or 5 nanometer give and take. That's what they're manufacturing now and developing process technology for 1 nanometer. It's getting smaller and smaller each of the unit or transistor. Here it's essentially getting bigger and bigger. It's not that we don't know how to make it smaller. It's just that each of the qubit, it's getting connected. If you remember all the wiring I showed at the beginning, from this tiny chip, all the outlet, we need to connect these thick wires and connect to everybody else. So if you want to put more of them, more wires, so you have to make them bigger and bigger. Now that all interesting parts are done, now let's talk about the boring part. So when I started studying quantum computing, I don't remember I studying quantum mechanics in my 10+2. Probably my physics teacher also didn't study in their 10+2. But whatever it is, I needed to start somewhere in layman terms. So this is how I understood quantum computing then. So if you think of a rocket, it has a position and velocity. And think of a noise cancelling headphone, it kind of have a constructive and deconstructive interference. If you humanize a rocket, so much of sound, right? Rocket would get irritated. Put a headphone on top of the rocket. That's a quantum computer. So a quantum computer is basically has a state which can be controlled, and the coefficients of the states are complex number that can constructively and deconstructively interfere. But at the end of the day, I'll bring it down to a qubit. But that's basically a quantum computer in layman terms that you can explain to anybody on the street. But if we want to talk to each of us, let's put them side by side. I put that just to show you classical and quantum. So in classical, we always talk about bits, on and off, switch. That's transistor. In quantum, it's kind of 0 and 1 at the same time. That's what we call as qubit. Now, if you want to visualize it, Schrodinger had that analogy of a cat. You put a cat inside a box and then put a smart mechanism that would open the lid for the poison. If cat is smart enough, it would open and drink and die. If cat is dumb, it will not be able to open and will not die. Now, if box is closed, if I ask you, can you tell me if the cat is dead or alive? Let's say it's a soundproof box. There is no way you can answer it because you don't know whether cat is dumb or sleeping at that time. You have no idea. So that only thing you can say, I don't know, it may be alive, maybe dead. So that's the idea of 0 and 1 at the same time. That's again layman terms. And Feynman said, never take an analogy from a classical world to explain a quantum phenomena. So any example I'm going to tell today, those are actually all wrong. But what is right, that a qubit will be a superposition of 0 and 1 at the same time. The easiest way to visualize, think of it, it could be 80% of 0 and 20% of 1. So if you think of alpha as the probability of 0 and beta, which is 1 minus alpha probability of 1, so alpha square plus beta square is equal to be 1. So it's not 1 minus alpha. So that's basically 0 and 1, that's superposition, that's qubit, that's the power. Now, if you think of computing ability, if you put more and more transistors, computing ability increases linearly. Although you will disagree with me, that's not really true. I can put 10, 20 cores, multi-core computer, but if my compiler is not good enough, if I don't have parallelism, those cores are not doing anything, therefore it's not really linearly increasing. That's true. But let's assume you have an infinite parallelism. In a classical computer, you get a linear growth by adding more transistors. But in quantum computer, because all the qubits are talking to all of them are all at the same time, gossiping, if you want to think about. So computing ability, if you have n qubit, you have 2 to the power n computational probability. It's actually better than that. Because although throughout this talk, I'll talk about qubit, I'll talk about it could be 0 and 1 at the same time, but there is also notion of qdit. If you can control it, I'll come in a moment, what do you mean by control it? If you can control it, you can get 3 at a time, 0, 1 and 2, qtreat. Or it could be any d dimension, qdit, depending on how you control its energy state. So then if it's a dimension of d, and you have n qubits, your computability is d to the power n instead of just order n. So that's the ability, but that itself causes the problem, because if everybody, think about it, I'm talking and at the same time all of you start talking to each other, what would be the outcome? Same story here, it creates a lot of noise. Now, noise is a problem in classical computer. If I try to present this to the people in semiconductor process technology or anybody working in the back end and say, oh, noise is not a problem in classical, they'll kill me. They spend all their life trying to control the noise in this nanometer regime. But in classical, it's even worse. It's actually exponential. The advantage that you get here, all of them become a disadvantage here, exactly disadvantage. And because of that, in today's quantum computer, even doing 2 plus 3, you are not going to get a 5. Forget about who told you what. You are not going to get it. You have to try again and again and again, and there is a probability you might get it. And then finally, which is there is a misconception about applicability. Everybody has a common notion that quantum computer is going to solve all the problems in this universe. That's not true. In fact, it can only solve a class of problems. If you took computational complexity, it's basically BQ, there are classes, different classes, P, NP and all that. There is a BQP, BQC kind of class. Only those classes of problems, quantum computer is good, suitable, better than classical, whichever way you want to put at it. And the people who are using mostly, in a lot of people in particle physics, in chemistry, they want to have detailed simulation and optimization. It's ideal there. Let's say somebody is trying to figure out a particle, how suitable it is to cure a disease in a human body or how much it gets absorbed. As of today in a classical, we are doing approximate and we are doing living with it. Let's say you buy an anti-aging cream. I never buy, I don't suggest you buy it. You put it on your screen. Who cares whether it's really doing anti-aging or it's doing 100% of it? That's the classical world. But in a quantum world, if you kind of evaluated it, and if it says it's going to make your skin look 10 years younger, it will make it 10 years younger. That's the difference. Do you need that precision? Do you need this accuracy? Do you need all these exponential computation? Then quantum is the solution for you. Otherwise, you can spend rest of your life trying to solve that problem in a classical problem. Any question on classical versus quantum? One last thing that I normally don't talk about, classical quantum computing, or let's say quantum computing, is more like FPGA. All these qubits, think about tiny dots in that chip you saw, those dots are placed there. You can program them the way you want by sending electrical pulse. When I talk about quantum compilation, I'll touch that point again. But it's not like a classical processor where you send instructions and it starts computing something. It's not a prefabricated hardware. Think of a free floating agents. They're actually not floating, they're fixed. Those agents are sitting there. By sending pulses, you can make them behave. You can make two people talk. That's entanglement. You can construct gates. And 2 seconds later, you don't want it. They're back to doing nothing. Technically, they always create noise. But that's the kind of distinction. So once we are done with this, now let's talk like engineers. If we are engineers, like computer engineers, if we are doing classical, then we are going to have some Boolean circuit, some AND gate, some XOR gate and all that stuff. And we represent using truth table, inputs and outputs. In quantum, the analogy would be, it would be quantum circuit. I'm not going to go through all these, whether Hadamard gate or not, but there would be quantum gate, and there would be this kind of entanglement, and there would be definitely input and output. And here the 0, we kind of have this cat notation. We don't write 0 and 1. We write this vertical line, then a slightly bent line, and then put 0 and 1 inside. And output be some kind of combination. Now, I want you to understand that here, this circuit, I want to map it to the quantum computer. Here, definitely, it should be obvious to you, we need 3 qubits. One to create this Hadamard gate, another to create this Hadamard gate, and 3 qubits here. Now, do I need 5, or out of these 3, these 2, I use few second, millisecond, nanosecond later, that can be configured. So using 3 qubit, you can construct it. You have to program them by sending pulse. And these 2 are, you are entangling them. So there is also a pulse you create and say, hey, you guys should talk. You send a pulse, so they start talking. That's basically connectivity. Now, this also can be represented using something similar to truth table, but in that community, or if you took linear algebra, this is unitary matrix. But you can see there are also complex number there. And if you recall the state, I define quantum state by saying it has it has a state of something, and it also has constructive deconstructive interference. So that's basically this whole story. So you can do quantum computing without ever touching a quantum computer by simply in the linear algebra domain, because at the end of the day it will look and feel like you are doing a set of matrix manipulations. When I start talking about algorithms, then I break it down to circuits. It's a bunch of matrices you are actually manipulating. It's just that it would have some complex number, a little bit more involved mathematics, but that's what it is. We can live on that. Yes, please.
I understand what is the, like, why are they communicating? What is it?
So why are they communicating? Actually, it's the other way around. That's the beauty of quantum computer. Superposition, they can be 0 and 1 at the same time, and entanglement, they can be entangled. Because these two actually, there are few more, these two actually gives this whole supreme power that quantum computer in the best possible scenario, non-noisy scenario, produces all these great effects. That these two are the fundamental building block. Right? But if you want to think from why am I untangling, the better way to you visualize, although that's not technically correct, two gates are producing something, you are feeding to a third gate. This entanglement, you can think of a third gate you formed, although you realize that's not technically accurate. Now, what is happening over the years from 1998, number of qubits in a processor are increasing. I forgot to plot 2023 December, that's about 1000 qubit system from IBM. Now, as you can see, 433 is actually not a small number. It can compute 2 to the power 433 states. That's a lot. You can do a lot of computation. Now, going forward, this is expected to be the story. Now, even today, we call it noisy intermediate scale. Things are very noisy. I'm going to briefly talk about quantum error correction. But in briefly, until quantum error correction occurs, we have to live in this noisy world. When things are not perfect, you have to run same experiment hundreds of times. You have to rely on probability. But even then, there are classes of problem that's kind of flourishing. Quantum machine learning, which is what I'm going to talk today. Quantum sensing, quantum communication, they actually works like a charm. And just going back to your answer, so entanglement, I mean, in India, we believe mom kind of feels if a kid is sneezing, that's actually entanglement in classical world. But here, literally, you can entangle and take one of the qubit and places in Australia, another qubit in Bangalore, and then anything you do to this particular qubit, same thing will happen to the other one. Now, of course, there is all this controversy. Einstein didn't like it, that how can it happen? Things moves faster than light. I won't get into that. We can talk offline outside the thing. But this entanglement allowed that communication. And there are published literature to show that Chinese president actually uses quantum communication to talk to their mafia. Now, we don't like mafia, they're buddies, whatever you like. Okay, so now fault-tolerant quantum computing is basically what we are expecting to happen in the future when you have a lot of qubits. I'm going to talk quantum error correction in a moment, but in layman terms, if you have 5 qubits, 4 of them will help each other, the 5th qubit, to behave fault-tolerant way. Then you don't have to worry about noise anymore. But that kind of creates a tricky problem. Why we can't do that today? Because simply divide, except 433, which we can't use, 127, if you pay, you can use from IBM. Some of these are free, 2, 7, 12, I don't know about 50. But 127, roughly, each minute, it would cost you roughly $1,000 if you use that computer. I'll come to that in a moment. How do we do results? So if you have 127, you divide by 5, give and take, you have like 20. 2 to the power 20 is not a lot of state. It's not a lot of computation you can do. That's why we are doing this kind of computation. But in the future, when you have quantum error correction, pretty much sky is the limit. Like classical computer, you can do anything. When would this happen? I don't know. Now IBM is coming up with this 1000 qubit. Then they are saying they will have a multi-core. 2030, they will have probably this. I don't know whether I'll be alive, so I can't say anything. what will happen after I'm dead. Now I'm going to briefly introduce quantum algorithms before I move forward, because we are trying to do machine learning on top of it. Now quantum algorithms, when you hear, first thing to comes to everybody's mind, oh, that's source factoring. When if time permits, I talk about quantum security, I'll come about source factoring. Grover search, instead of searching in a database or unstructured database, instead of taking order n, it will take you square root of n. So I'm not going to talk about that. Instead, I'm going to talk about an algorithm, very simple algorithm I developed. I'm not saying it because I developed. I wanted to walk you through the steps how I came to this developing this algorithm. Because I don't know how Shor or Grover came up with that solution from zero. So we are trying to do clustering, and clustering is pretty much everywhere. Whether you are doing the MRI image of the brain, or looking at whether it's Facebook, Orkut, whatever it is, when you are looking at, or even Google doing this page rank to find out which pages to print in front of you when you are searching something, it's basically doing some form of clustering. And when you do this clustering, one of the popular clustering technique in classical domain is known as spectral clustering. And basically, idea is very simple. If this is a person, how many people are connected, that's a number. So that's basically they are related by one edge. And so you kind of define and who is related and who is far, who is close, you kind of define and cluster. If you want to do that clustering, of course, you create a graph by saying who is connected to whom, adjacency matrix, you solve the equation, and if the numbers are similar, we are talking here two cluster, it could be many cluster. If numbers are closer, that's in cluster, number are far, that's in a different cluster. And the way the algorithm works, construct the adjacency matrix, find the eigenvalues and eigenvectors, plot the eigenvectors, and you got your clusters. If you do it in a classical machine, it's order n cube in the number of nodes in the graph. If you think of Facebook with millions of nodes, so you do the math, million to the power 3, you can forget about it doing that. If you put it in a quantum computer, it's a linear time complexity. I just want to tell you, what's the catch? What's the magic? How did order n cube become order n? To do that, I hope you are not COVID batch. You've actually seen this page in your 10+2. If you've seen this page, wherever it is, sometimes it's physics book, sometimes in chemistry book, it's not important. It's showing the hydrogen wave function. Again, layman terms, electron rotating around creates magnetic field. You can think that way. Or you can go by Heisenberg's principle, try to figure out the probability of finding an electron, whichever way you studied physics. It doesn't matter, it will give you this spectral kind of graph. Depending on radius, angular momentum and projection, it will going to give you this kind of graph. These numbers are RAP numbers. But the part that is important for this discussion, that if we can control any of these two wave functions, we have a qubit. Although hydrogen wave function is hard to control, that's why nobody built a quantum computer using hydrogen, superconducting qubit, quantum dots, those are, but the idea is, each of them, this nice beautiful picture you see, they are computing eigenvalue inherently. So if you can send them pulse, orient them in a right direction, then just measure, you get the eigenvalue. Because inherently they are computing eigenvalue and eigenvector. Why am I saying that? Because if you go through this algorithm and I zoom into this spectral clustering, this is our quantum circuit, I'm going to ignore. If you look at the eigenvalue computation, if you want to do in a classical processor, it's a really huge equation. It's going to create thousands of instructions that you need to run in a processor. That's the order n cube story. All of this computation I can simply replace by sending electrical pulse to a qubit and then just measuring that qubit. That's it. Today it's in the order of nanosecond. Done. We got a big function you computed by doing that. What's the bottom line? That means after doing this, I realized that any quantum algorithm or any algorithm which has eigenvalue computation, quantum is ideal for that. It doesn't have to be spectral clustering. It took me some time. It's always find the solution, then you figure out, oh, why didn't I think of that? Any algorithm, even in classical world, if you have a kernel or some important computation that is eigenvalue computation, that should be your antenna on, oh, now I can use quantum computer. I can program the qubit, measure it, I get the eigenvalue. It's a little more involved than that because qubits don't like us. Anytime you touch a qubit, it collapses to 0. It's not going to show its value. So you have to do some operation on it to kind of know what it's doing. Those of you who have kids, you know, they will be really mischievous, but when you try to hold their hand, they will have big sparkly eyes and you're like, you will feel guilty. What am I telling my kid? Right? That's basically qubit. Now, this I already talked about, so I'm going to, so that's the whole idea of order n cube versus order n in layman terms. Anybody has questions on that? So after development, I figured out I didn't do anything. Yes, please.
So you said that we measured the qubit. So you said basically then what happened about the Heisenberg principle?
Right. So that's, as I said, again, we can talk offline because measuring is that I skipped the quantum circuit we developed because we have this whole thresholding logic and quantum Fourier rotation. We are performing an operation on it, and that operation result is saying what was the value. Direct measurement, there are measurement circuits, direct like this kind of apparatus on the quantum, that chip itself. But if you do a direct measurement, it's going to give you a 0. You are not going to get that nice distribution of alpha 0 plus beta 1, that you are not going to get. And that's exactly what we wanted because that's the eigenvalue. Any other questions? Yes, please.
How many iterations you are running this quantum algorithm for?
Oh, that's an interesting question. So you have to hold for a few seconds before I talk about quantum measurement. But if you are doing it right, it's 3 to 5. If you are doing it wrong, hundreds to thousands of iterations to get a good fidelity or acceptable result. In this case, at least we know the result. The people who work on quantum chemistry or all that, at least we know what is the ground state by using your NumPy solver. So we kind of know, okay, now we got it. But for chemistry and all that, you don't know what state you're supposed to reach. You don't know the lowest energy state. So that becomes much harder problem. Again, we discuss all of that offline. Yes, please, because I want to start quantum AI.
Do we have to reduce every computation to eigenvalue computation?
No, because only insight I wanted to give that after walking through all of that, I figured out, oh, any computation which has eigenvalue, quantum is ideal. But if you look at source factoring algorithm or Grover search, it doesn't make use of that. It uses some other features. It has many other interesting features.
So this is it similar to the HHL?
What is HHL?
Harrow Hasidim Lloyd. That's to find eigen.
You're finding solution of linear system equations.
Could be. I don't know the HHL. I can look at and answer that later. Okay, now I'm going to talk about the main part that I wanted to do, quantum as artificial intelligence. And I want to apply it on a specific problem. But before I do that, I want to just connect the dots and give a big picture. And the big picture is, if you look at computation, we are talking only classical and quantum. There are many other spectrum. Even if that, because classical and quantum, two symbols, we have 4 possible scenario. So CC is, you are doing a classical algorithm or classical computation on a classical data using classical computer, which is what most of us do all the time. That's the CC. Then we have QC, where you have a quantum data, and you will see example, quantum computer produce certain data, you are analyzing using your classical computer. That's the QC kind of problems. And there are many classes of problem there. Then CQ is basically you have a classical data and you are basically doing quantum computing on top of it. And QQ is you are dealing with the quantum data and quantum computing. So most people when think of quantum computing, they think of this one. But I want you to know there are other variations. Classically in the domain, these two combinations are known as quantum machine learning. Now, as you can figure out, this has two flavor. Quantum is helping the classical. Another flavor is classical is helping the quantum. What I wanted to show in today's lecture is this one, QQ. Classical is helping the quantum. Now, before I do that, it's only for a class of problems. Remember, quantum you cannot apply wherever you feel like. This classical helping the quantum, people have demonstrated on variational quantum algorithms. So, as the name suggests, it has some parameters inside. And if you want to visualize this, think of a sorting algorithm or any function that has parameters. So, you have a sorting function you want to call, and you put 1, that's probably does insertion sort. You put 2, that does bubble sort. That's very gross example. If I zoom in further, maybe bubble sort itself has, each of the loop has some parameter. That's the way to visualize. So these algorithms are parameterized algorithms. The spectral clustering I showed, that's a fixed algorithm. It has no parameter. But a parameterized algorithm, and where is it used? It can be used everywhere. Everywhere. So this is the variational algorithm. If I want to further simplify, it will look like something like this. You have a functionality, bunch of gates, you apply input, you measure. Only thing I put this theta and all that stuff, that basically means this gate. If I take classical example, you have AND gate, OR gate. Think about this gate can behave like AND and OR based on its mood, based on the pulse you send. This should remind you FPGA. You can program it to whatever you want, each of the lookup table. So it's similar to that. This is a qubit. You can map, technically it's not accurate, it could be more than a qubit, but 1 qubit, you can program it to perform certain gate of certain strength. That's the parameter. So initially you start with something and then you measure, am I doing right? Then you ask the classical computer to do some gradient based optimization, and think of this as a machine learning. That's where the name came from, quantum machine learning. And that machine learning will tell you, you are going in the right direction or you are going in a wrong direction. And then it's going to give you feedback. And accordingly, parameter gets updated. So that's the whole story of classical helping quantum in the sphere of quantum machine learning. Any of you have any questions with this story? This is an algorithm, no matter how I showed, this is a quantum algorithm that is parameterizable, and classical optimization routine, by looking at its behavior, guiding, you are going in the right direction, you are going in the wrong direction. Take left, go right, look up. Yes, please.
So we can know whether we are going in the right direction or wrong direction, but we don't know whether how much we are accurate.
That's where the interesting question. That's why it needs all these iterations. If you are absolutely correct, then 1 iteration will finish it, right? Now, of course, in this case, this is, I'm talking about accurate one. You tried to form an AND gate, it became an OR gate because of the noise. So that's going to create all these problems. Classical optimizer doesn't know that. Then you have to give that error model. Error model may not be accurate. And just for your knowledge, these qubits have its own personality, like each of us. So every qubit is not going to behave exactly same way every morning. I literally mean it. Every morning. You have to characterize them. Then even if you are using a 127 qubit computer, one fine day, IBM might say you can use 70 of them. Nobody will tell you what's the other thing. They are not in a mood to do anything that day. But in engineering terms, they tried to characterize them, but they are not giving good fidelity. That's why IBM disabled it in that morning. I don't know whether they do morning, noon, afternoon, evening, because you submit the job through the cloud, you may not get immediate access. So long story short, this iteration comes from many possible variations. Yes, please.
Generally, when we run this quantum circuit, we might be ending up with different measurements, like some errors occurs. And in that case, when we perform the classical optimization, we might be going into some other local optimal point.
Absolutely. This is, I'm not an ML expert. This is not an ML course. All those are absolutely correct. Absolutely correct. Even in idealistic world, it needs multiple iteration. If it's in a wrong, then it's all going to be, this is gradient descent, local, whatever it does, it does. So this is classically known as ansatz, but I want to introduce the notion of the application I wanted to show, state preparation. The whole computing itself, let's say you are doing a sorting algorithm running in a computer. Eventually what will happen? The results would be sorted order. If you ignore that computation, this could be viewed as a state preparation problem. It's just that you have to know the final result. If you know the result, put your initial values in your register. If you know the final result, put the final result in your register. You don't need to run the instructions. I know it sounds silly. If I knew the final result, why am I doing all this hypocrisy? I get it. But this is a state preparation problem. You prepare the state, then you do the measurement. Then classical, based on that measurement, does something, you prepare the state again. I know it sounds funny. It seems like there is no computation going on anywhere. But technically it does. But it can be simplified this way because I wanted to show you how state preparation can be done efficiently with the help of machine learning for the quantum circuit. If I am to simplify even further, all these complexity I removed. So you need to prepare the state, compute and measure. And this should be same as classical. You initialize, program counter, register, translation, look aside buffer, all that you initialize. Then you run the program, then you look at the result. It's same analogy as that. So I'm going to focus on the state preparation. So the first question you want to ask yourself, how is state? Rigetti is one of the, I won't say competitor, another quantum semiconductor qubit bed company. So they sell this product, a quantum eigensolver solution product. They had as a quantum processor and a classical processor. Quantum processor, you prepare the state, measure the term. Classical processor, you compute the answers and then give the feedback, which is similar to the previous one, but this is their patented technology. So this is also commonly known as classical quantum hybrid algorithm, which is rest of the world called as quantum machine learning, which is same, computing the variational quantum eigensolver. Now, how do people do state preparation today? So the way people state preparation, they let it cool down. Remember, it's very cold ambience. They let those qubits cool down. You can't cool down too much, then it would be like gone. They are not going to work. Remember, these are superconducting qubit. Or if it's not cooled down enough, they are going to be in agitated state. So cooling down. But if I am angry, what do? You put me in a room, close the door, right? How long? How do you know I'm not going to looking for a ceiling and a rope? Everybody is adult here, right? So that's the mechanism. It's just that you don't know how long. So to avoid that problem, another problem is this cooling mechanism, or known as passive reset. It can take you to only 0 state. But the system you want to initialize, whatever the classical machine learning told you, that may be an arbitrary state, combination of 0 and 1, superposition. Then you have to apply further gates and to get to a target state. So in an active reset, which is slightly better idea, which basically says, well, we put Prabhat in the room, but we are not sure whether he's actually getting cooler or he's getting angrier, right? Becoming a bomb the moment you open the room and blast. So then you constantly measure, open the door a little bit and see what happened. You measure that with the classical computer and then let it cool a little more. So you try to figure out when the state is initialized. Problem is, you introduce classical computer, all these supreme advantage you wanted to get from quantum computer, it's all gone. Even state preparation, you introduce the need for classical computer. And this classical computer is not doing quantum machine learning. It's doing still state preparation. So that's not a good idea. So I observed something, we came up with this idea. I observed how mafia culture works. If I want to take some money or donation from you, I have to threaten your neighbor. I may have a deal with them. Actually, I'm not threatening. So then you get scared and you pay the whatever, bribe, whatever it is. And Schrodinger came up with this idea in quantum systems from physics perspective, theory perspective, almost 50 years ago, before 50, 60 years ago, actually long ago. The idea is that if you have a system qubit, you want it to go to a target state, you entangle it in a special way, not normal entanglement, with another qubit, we call it auxiliary qubit, and keep irritating it by measuring it. You keep on measuring it. Eventually, it will go to the target state. I know there are a few funny facts. I'm going to answer offline because it's going to take a long time, or you can read my paper. First of all, this system qubit doesn't know where to go. It's like mafia is threatening somebody. I don't know how much to pay. Should I pay 100, 200, 500, 1000? I don't know the target state. It will go to the target state in quantum system. Second thing is this measurement, I don't care about the value. Simply the act of measurement will guide this one to the target state. That's the notion of quantum steering. What we showed, whatever Schrodinger proposed in the theory, we showed this actually can be implemented in a modern quantum computers today with qubits and all that stuff. But this physics, quantum mechanics story of quantum steering, I didn't invent, that existed. So one other thing I want to tell you, if you are from computer science, in physics, somebody doing theory, somebody actually showing it works, both are equally valuable. So even if some theory exists, don't get demotivated. Try to show whether it works in modern quantum computer. That actually very powerful. So that's the state preparation done, and we kind of show that it actually works on different kind of IBM quantum computer. We kind of showed all of that stuff. Now we also improved it further to show that even this passive steering, even when you are steering and you expect it to go to the right place, but what if it's not going to the right place? Then involving classical, then we kind of published more on random. You know how academicians are. They just keep publishing because otherwise they're not going to get funding, and you know the rest of the story. So I'm going to skip rest of the story. But one thing important, when you want to publish, you cannot just say, I have this great idea and I'm going to publish. People are going to say, how is it working today? Even this, now I'm coming back to quantum machine learning. How is it done today? Those of you started working on quantum, first thing you want to do is, there is a tool called KIAC from IBM. You can think of it as a simulator, compiler, or all of the above. It also has a notion of variational quantum algorithm, and which can do everything for you. Classical, quantum, everything is all there. So if everything is there, then what are we inventing? Why would sponsor give you the money? So you have to come up with the storyline. Let me tell you the storyline. So it took us time. We had the solution, but we didn't know the problem. Because to publish, you need to have a problem. You realize, right? So we're looking for the problem. And then we figured out, and by the way, looking at anybody else's code is the worst thing in the world. Some of them may not be even alive today. So you can't ask anybody. And then there is a company secret policy and all that stuff. So we figured out that this KIAC has a state preparation, but for state preparation, you need to give a good starting state. So I'm asking somebody to go to Mysore from here, but they're saying, well, you need to put me in Vidhan Saudha, then I can go to Mysore. If you put me in a random place in Bengaluru, I don't know where to go. That's literally what was happening. It took me almost a month to figure that out. There is a hard tree for computation. Mathematically, that can put you in a reasonably good state. Then KIAC works like a charm. But if you don't put it in the good state, and that was our talking point. But anyway, I'm going to skip all of the detail. I want to show you the result. So if we use Python NumPy solver, and this is for the hydrogen ground energy, exact value would be here, this orange slash whatever brown line this is. If you are using UCCSD, which is one of the function in KIAC, or quantum simulator, if you may, that's going to give you this kind of green line. And the passive steering is basically what we propose. That's basically that line. Clearly, this is the result. You cannot publish. You realize, right? You doing same as state of the art. What's the point? So then we realize that for passive steering, we can start in any arbitrary state. I don't care. But for KIAC, you have to put it in a good reference state. Like put me in Vidhan Saudha, then I know how to go to Carbon Park. But if I'm trying to do state preparation, and then you are asking me to put in a known state, how do I? It's an infinite loop. Although for small qubit system, there are functions called Hartree fork and all that mathematical functions that can do that. But when you have large systems, complex scenario, there is no way you can find a good initial state. But nonetheless, this is where machine learning came handy, and all this work I kind of showed you are basically the quantum AI problem applied to quantum state preparation. AI is helping us to guide in the right way through that steering mechanism. You are steering, and then machine learning is telling you, are you steering in the right direction or wrong direction? Remember, in theory, it's supposed to go in right direction. If there were no noise, probably, I can't say that because I'm recorded, probably machine learning would not have been needed for this application, the state preparation application. But in reality, we are using it, using classical machine learning to guide quantum computation. So remember the 4 quadrant I showed? This is the QQ problem. Any question? So the class of problem, this is a class of problem within that bounded quantum polynomial time problems. The problems that are ideal and suitable for quantum computing, but not so much good for classical computing.
Great. So you have told that you are using classical machine learning to help your quantum.
Do the quantum state preparation.
Again, you told this is QQ.
This is the QQ.
That was not contradictory. QQ was quantum data, quantum machine learning.
So it's not a quantum data we are producing. We are doing quantum computing. And our algorithm is also quantum. We are running in quantum computer, but in the inside there, it's using classical machine learning. Now, because I have 10-15 more minutes, I'm going to talk about design automation. This is for engineers only. Yes, please.
Just to clarify, to follow up on that question. So you're converting classical data that you want to process into quantum data using your quantum state preparation, and that's you're using a quantum computer to process it. Hence, it's QQ.
Right. No, we are not taking classical data here. We are doing quantum computation. Let's say you want to go from point A to point B. Nobody produced data yet. Those are, if you think that's the classical data, then that is. But in the CC and all that, classical data means you have a tons of data. Let's say you are doing a searching an element in an unstructured database. You have lots of data. Or you are training some machine learning and you get millions of images. That's your data. In that sense, we don't have that kind of data here. But during this computation, it will produce a lot of data. That's also quantum data. And we are using that variational quantum algorithm running on the quantum computer to process that data. That's why it's a QQ problem. So now I'm going to talk about design automation step. It would be easier for you, those of you kind of worked in classical processor or VLSI domain. You start with some algorithm. Let's say you write a C program. You compile it, you get the binary. Then you run it on the processor. That's for the software side. For the hardware side, you write some VHDL, Verilog, system C code. Then you synthesize it. You get a gate level netlist. You further synthesize it. You get some bunch of transistor representation. Or you get a layout. Then you fabricate it. Then you get a chip. Or you compile the VHDL Verilog, map it to FPGA. You generate bit stream. And then you map it to FPGA. So this is analogous to that. So let me start with quantum compilation. This will give you the full picture, how the full stack of quantum computing works. So you have an algorithm. I took the example of clustering algorithm. It could be Grover search, any algorithm. People use different, and then you have some set of constraints. And in compiler, if you worked in compiler, you know that constant could be anything, number of qubits available, how far they are, how noisy they are, and all that stuff, how quickly you have to finish, all that constraints that are out there. And we use the language Rust. It doesn't matter what language you use, but then you use compilation. So there are many classical well-known compilation techniques such as cosine sine decomposition, Slovoky-Kitev algorithm. This is basically heuristic based. This is optimal and it should be obvious to you. If the algorithm is complex, then you want to go for this and you should be willing to take a pathetic result. And then you get a quantum circuit that I showed earlier, which is analogous to a gate level implementation. I'll be happy to give my slides so you don't have to take pictures. I'll give it to Professor Mandal and he will distribute to you. So quantum circuit, and then the second part of the story is similar to FPGA mapping. Now that you have circuit, I need to generate electric pulses. I'll show you example of that. Electric pulses to run on the real quantum computer. Remember, we use it through the cloud. And those pulses are kind of textual description. We don't touch that machine. We submit in the job in the cloud. It goes through somewhere, and then eventually it gets applied. And or you can even apply the Qiskit simulator. Your Qiskit simulator running on your classical computer, you can apply and it should work perfectly fine. So you can use your Qiskit, that's free, or actual quantum computer through cloud. In fact, even if you work in IBM TJ Watson, you are not going to that computer room. You are sitting in a computer, sending that data, character analyzing, it's going through internet and whatever to that quantum computer. So it's pretty much the same. It's just that they get instant access. For us, it takes time. Anybody has a question on this flow from beginning to end? I'm going to zoom in one or two areas only.
Sir, one.
Yes, please.
So, when you say that quantum circuit is being formed, right? How does it translate to the chip that you showed in the beginning? Because I would think that this quantum circuit is something analogous to an FPGA where all the circuits are being programmed, like all the gates are getting programmed. But how does that translate to the various connections that go through the chip?
Right. So
every program will have different configuration.
Absolutely. So I took a wrong portion of the thing. I should have zoomed into that chip that was somebody holding. So think of that chip. Think of 4 dots. Those are the 4 qubits. So you want to map this to 4 qubit. Clearly we need 1, 2, 3, 4, 5, 6. Also in terms of depth, we know 1, 2, 3, 4, 5, 6, 7, 8. 48, almost 48 qubits would have needed. So then there is a notion of circuit partitioning. Now you have to assume that it fits in a it's exactly like IBM days in 1950s and 60s. The computer was so small, they have to manually divide the program, load little bit of the program and little bit of the data, then get the result, then that result and remaining program. And so this is similar we have to do today. That's like 1950s and 60s and IBM. That's what you have to do. Coincidentally, this is also IBM. Now, what is happening? Your observation is perfect. This is FPGA, 4 qubit sitting. What you want to do with it, it's up to you. So typically what happens, you want to generate electrical pulse to program this qubit. And then you need electrical pulse to kind of say that this qubit should talk to this qubit. So you have to keep sending pulses and they have to get programmed. And because physically they are separated, some qubit very far away, it's not actually trivial. You need swap gate. It's a lot more complicated. You can talk offline, but it can be done. And fidelity goes down. If you want 3 people to talk, but you are talking to somebody and then that person talking to somebody, when you hear what they're listening, that's not what you said. It's kind of garbage at that point. But all of those are sending electrical pulses and programming those qubits that are sitting there. So I have 5 minutes. So I'm going to show what happens. So gradient ascent pulse engineering, no matter how interesting the name suggests, it's basically send random pulse and see what happens. And then you kind of compute the gradient, again AI, compute the gradient and find the one where you have least noise. And that's the pulse. Now again, compiler, how many times it should try and what will happen. Some of these IBM or whichever company's processor you are using, they will tell you certain kind of behaviors and mood swing and all that. They will tell you that this qubit did not do the exam well and not feeling good today, don't ask any questions. All that you will know. Now here is a CNOT gate just to show you when we get the result back, how do you know what you are getting? If you want to visualize, so if CNOT gate is kind of working, then this should have been yellow, this should have been yellow fine, but this should have been yellow and this should have been yellow. And the way it works, this is exactly how electrical pulses looks like in exact those dimensions, time and amplitude. And those are, and basically if you take a picture of that or get some data, so this CNOT gate is correctly formed. That's how we kind of know that it actually worked. Of course, the time it takes to go, come back and all that is a different story.
So here 2 pulses have been propagated, red one, blue one.
These pulses?
Number of pulses are 2 here.
In this case, it's 2. Because it's 2 inputs. So we are trying 2 qubit machine. We are trying to program those 2 qubit 2 pulses. But this is just an illustration. It could be more, less. It could be time multiplexed and all that. Now, lot of research can be done here, and like we came up with the idea of quantum compression. I'm going to skip all of that. And again, all of that also has the notion of AI. Any of them you do, you take it to the kind of different dimension and then reduce, and a lot of algebra, lot of AI. Now I want to just talk about briefly quantum measurement. I talked about state preparation, computing, you kind of know, and the measurement is also noisy. The way qubits are noisy, even measurement is also very noisy. So that measurement also uses AI, although that's not classically known as quantum machine learning, but I want to show you how quantum measurement is done. And most of the publications you should see today, they don't talk about preparation, that's why I focused. They don't talk about measurement. Most of them talk about this space right here. And most of them assume no noise scenario, which is fine. As a starting research, you can assume ideal story, but eventually you should take it to a noisy realistic world scenario. So the goal of this measurement is how do I get accurate result in least number of iterations. That's the goal. How is it done today? So the way it's done, depending on the number of outputs, and in that community, it's called as discriminator, which is basically classification. Did I get 0? Did I get 1? And then you kind of do those discrimination, and you do n classification to figure out what did I get. And then of course you consider the probability and all that. This example, you'll think, okay, probably I got a 0 here. But what we tried to show that how can we do better? What we are saying is let's take all these measurements and create a distribution. And this idea came from statistics. where there is a notion of cumulative distribution function. Instead of treating each element as an independent probability and figuring it out what they are and then trying to find out average or whatever, we just treat them, they are part of the same circuit, same design, same output. So if you can fit to a distribution, then and you in a single classification you will get better result. That's basically the key idea. And pictorially, each of the qubit you measure, you get a blobs of data. And each of these data basically represent what percent 0, what percent 1. That's alpha 0 plus beta 1. That's basically where alpha square plus beta square equal to 1. So that basically, if you do a cumulative distribution function, then you get accurate result much faster. And again, if you want to talk about it, I can talk offline. I want to just to quickly take 1 minute each. Is that okay? 3 more minutes. So quantum error correction. So error correction, we take it for granted in classical domain today. But in quantum domain, we have two big problems. You can't copy, you can't touch. The touch me not, the plant I always played with in my childhood. I found it in Florida also. So any measurement collapses a state of a qubit. If you want to measure it, it becomes 0. You don't get the value. Because that would have been nice, that you measure and keep it, and if things gone wrong, you copy it back. That's what we do in classical computer. Shadow registers and shadow table, shadow this, shadow that. We can't do that. We can't copy, we can't touch, we can't measure. So then there are other ways of doing it. One of the popular coding technique, but we still have a coding technique. The way we have error correcting codes in classical domain, they call as surface code. But surface code has its own problem. But anyway, so a lot of research problems people solve around it. If you want to work on quantum error correction, so two areas are very popular, are going to stay for a long time, even when I die: quantum error correction and quantum machine learning. And those are very hot areas to get in. Other areas good too. Quantum verification is an interesting area. In fact, there was a PhD thesis from Berkeley after 8 years, one paper, which basically proved quantum computer actually doing quantum computing. 8 years. And it took me 6 months to even understand that thesis. There are other interesting problems too, same as classical computer. You have an original algorithm, then I gave you a circuit. Can you tell me, are they equivalent? How do you prove? Remember, dimension is very much higher here. Those of you who work in digital domain or software domain with sequential model, and you go to concurrent model, a digital model, that's so much more complex. From digital or discrete model computation, if you go to continuous like analog, it's like exponentially more complex. Now from analog to quantum, one more dimension, actually at least one more dimension, more complex. There are many approximations like Toffoli gates and all that stuff people do. Then you have to deal with false positive, false negative. Again, machine learning comes there. So I'm going to skip all of that. But two key ideas that I introduced in the community is basically quantum benchmarking. Most of the people, when they talk about benchmark, they only consider computing, like quantum volume from IBM and so on. So we basically showed that you have to worry about state preparation and measurement also, because any computation, including quantum error correction, it will do compute, reset, reuse. So how can you compare this quantum computer is better than that if only thing it does good is the computing? Because it's not, measurement is not once. Remember, in quantum machine learning, every iteration you are doing it. And in error correction, it's even worse. While computing is going on, you need to figure out which qubits are not working properly. You have to modify it while rest of the computation is going on. You can't stop any of them. So it's during computation, measure and reset needs to happen. And we also came up with the idea of quantum debug. So the idea is, if you computing in a quantum computer, which you can't touch, even if you're working in IBM TJ and you got a wrong result, what are you going to do? What is the rest of the world doing? Run again and again and again and see if it works. But what we are trying to say is, in classical, in software you can put printf. Here I can't do printf. So we have a notion of a model, and that model basically, we are trying to change that model so that it produces a data which is similar as that. Right? So in classical world we call it mutation testing. But the thing is, a lot of possible mutations, like if greater than 5, you change it to if less than 5, might produce the same erroneous value. But that's not useful, because hundreds of possible mutations can produce the same result. So we came up with a very interesting idea of Riemannian optimization, and I'll be happy to talk about, where you are guaranteed to have only one or two possible scenario. So basically it's a walk, it's a lot of mathematical paper, it's basically a walk on a Riemannian manifold. And then you basically go from point A to point B, and that's basically shortest distance. And that's a machine learning to kind of modify this model. And whatever this model is, that's what quantum is doing. Maybe one of the AND gate is programmed as OR gate. And quantum security is, I don't have time, but it's a very interesting problem. I started with source factoring, and that panicked everybody. US government invested, I don't know, close to $1 billion into it. But just for between you and me, don't tell anybody, we can factor today either 21 or 35. 7 times 3, or I don't know, what is 21? 3 times 7. That's pretty much all we can factor. But 8, 9 years ago or 10 years ago, when SOR came up with it, everybody panicked. Oh my God, RSA and all this, the prime multiplication based algorithm, quantum will break in no time, and therefore everything is unstable. While all this going on from prime multiplication based, then elliptic curve cryptography and all these algorithms came in, and then NIST started with this idea of contest that, okay, what will happen if we are in a world quantum computers are very stable? Then all security would be broken in no time. Can we come up with algorithm? And what algorithm in layman terms is lattice based algorithm, from prime multiplication to elliptic curve to this lattice based. But the unfortunate story is, after all this later, it selected 3 or 4 of them as the future, and the people who work in hardware security and looking at all this side channel. Even the day it was announced, I think the before that day, people published like tons of paper to show all of them can be broken. I know that's not a right way to finish quantum AI talk, but I also work in other areas, and it's not a coincidence I ending with. So I work in quantum, of course. I also work in trustworthy AI, cyber security, more focused on hardware security and malware, hardware verification and embedded systems. If any of you want to do PhD, here is my email address. Thank you.
Okay, time for questions.
Thank you, sir, for this session. I know it's a very vast session which is taken in compressed time. But there are some questions I have. That is, initially in the previous slides, you have shown that when we have 10,000 or 1 lakh qubits, we will be able to store data.
Quantum storage, yeah.
The QQ. But there is one theorem that you say that no cloning theorem. I'm assuming it is no copy paste. So how this storage will work?
So similar to quantum error correction, it's a roundabout way, but you will be able to store values.
Yeah, sir, I have one question that we are applying the classical machine learning to have the feedbacks.
Yes.
So suppose we have one negative feedback that the output is far away from the actual output. So what is the next step on the quantum circuit you are applying? That any update on the qubits or the algorithm?
Right. So in this particular example, the one I showed, state preparation, here quantum circuit or quantum computer is behaving as a dummy. Here active role is the classical computer, which is telling change your theta 1. Earlier it was 0.5, make it now 0.7. So quantum computer is behaving as a dummy system, passive system. It's simply programming it, and then the qubit, whatever qubit states are, measurement is going to measure that.
Okay.
So all of that boils down to sending an electrical pulse. The strength, amplitude, and all that of that electrical pulse.
Actually, can you explain a little bit about like trustworthy AI? Some qubits are having error, then how it will be trustworthy AI?
Okay, trustworthy AI is a totally different domain. It could be merged with quantum AI. Trustworthy AI has 2 flavors. Using AI for doing trustworthy computation. So on 9th, if you're coming for systems, I have a talk on AI, explainable AI for cyber security. But most people talk about the other way, trustworthy AI. If you have an AI algorithm, then can I trust it? From a fairness, and there are many other metrics, fairness, bias, and all that stuff, how trustworthy it is, the prediction it makes or whatever it makes, can I rely on it? When a car is driving based on an AI algorithm and stopping or not stopping, is that the right decision? So that's a different field. Now, if we merge with quantum, I don't think anybody studied that field. That could be a PhD topic.
Is a single qubit useful? Because
it is useful. So
but it doesn't have anything to entangle with.
You may not get much out of it, but you can do something and you can do nothing. And most of the people, it may sound funny, anybody from biology here? They study one cell for all of their life. One cell. In bioinformatics, in computer science, we talk about all that, whatever, pathways between lungs and heart, and we model and abstract. This is same as VHDL, very low compared to transistor. In biology, people just look at one cell, talk about its receptor, is it going to accept, reject, and all that chemical reactions. It's a lot of work. The people who work in material science, quantum materials, quantum devices, they actually deal with forming one qubit for all of their career. How stable it is, what's the fidelity, and do you need this, do I need supercooling, can I do it without cooling, all that stuff they do from research perspective. But if you're talking about, I have a quantum computer with one qubit, of course that's useless. But there is a whole variety of researcher just deals with one qubit, developing materials, devices and all that. Can I form a qubit out of it? Which is better than the technology we know today.
So in your spectral clustering approach, where you said that you have symmetric matrix and you want to find eigenvalues, eigenvectors, and I can leverage a quantum computer to make the cubic complexity to be linear complexity, right? But I doubt it is very difficult when you're trying to find a lot of eigenvalues, eigenvectors for a given matrix that is feasible, because most of the quantum algorithms we actually see about is about finding the ground state. Whether you talk about BQE or even to talk about quantum phase estimation, it is for a given eigenvector, I find an eigenvalue. So I would like to know your thoughts about using this QP kind of approaches for finding a lot of eigenvalues, eigenvectors, and will that be really linear scaling?
Absolutely interesting question. Actually, your insight is actually correct. These are all theoretically accurate machines producing accurate result. In reality, because of noise, even if theoretically you are getting order n, because you have to try so many times, so many iterations of state preparation, you will lose on everything. But the assumption is you are building a tiny island, I am building a tiny island on this ocean, eventually they will be connected and there will be an archipelago. That's the basically assumption, the people who are working in quantum computing domain. There are naysayers, they actually proved quantum computer will never work for anything. That's again, we can talk offline. Who are those people? And they're big names. They mathematically proved it.
Okay, any more questions? So if there is no question, we can thank Professor again. And there is a small token from KIAC.
Thank you.
Okay, so as I told, there will be a reward. There's a high tea outside, which is a classical one, by the way, not quantum one. So probability is 1. So please join for the high tea, and if you have more things to discuss, you will be available to discuss.
As long as you want, I'll be here. I'm also here until.
Yeah, so he's here till 10th of January. So if you want like detailed discussion, you can stop by anytime in our department. So for now, you can join for the high tea right outside in our CS Academy. Thank you.